we're going to talk about Diffie-Hellman Key Exchange now, which is a encryption technology that practically runs the internet. And it's got nothing to do with mayonnaise. So, let's go over how the internet works in case you haven't seen it from another video of mine. So you've got your computer with its IP address, and we're gonna call it 4.4.4.4, and you've got an ISP, and you've got the internet, and you've got the most important thing, which is a DNS server. And the DNS server takes addresses that are human readable, let's say like google.com, and converts them into addresses that are machine or computer readable, like 1.1.1.1. Because when you go to google.com, the internet doesn't know what you're talking about. It's gotta find a numerical address for the computer that hosts google.com. So when you request google.com, DNS server looks it up, gives you the address, boom, now you can go to Google. So if you're searching for cars, you tell your ISP, hey, I'm sending this message to Google. Your ISP forwards the message. Google sends you back car. It's just that simple. Well, no, it's not. It's way more complicated than that. But basically, this is how it works. And there's just one problem with this whole thing. The Russians can see all your data. So, in order to protect you from the Russians who are watching everything, we have to do some encryption. So now you have a key to lock up all your data, and so does the web server. And now the Russians can't see anything. And how does this work? What are the problems with it? Well, let's put it this way. You've created a key and you've locked up all your data and you sent it to Google. And Google's trying to open up your data. So it's asking you for your key. So you have to send Google your key for them to open up your data and figure out what it is you're talking about. So you tell them your key, and you can't encrypt your key with another key. You have to send your key in plain text, and the Russians can see the whole thing. So how do you encrypt data with a Google or with some other site and use a key and not tell them the key, or tell them the key in a way that nobody else can see it? And the answer is what we call a public key cryptography. And here's how it works. You, or Google in this case, makes a private key that only they know, and that's behind a firewall that's totally protected. And they use a private key to create the public key, which everybody can see. So when you want to send a message to Google, you encrypt everything with the public key belonging to Google, and Google unlocks the message with their private key. The public key only locks things up, and the private key only unlocks things. So the Russians can't see your data. So you want to send a message to Google, you say, what's your public key? And they tell you it's 12345. So you lock up the data with the public key, send it off. Russians can't read the data. Google takes the private key, they unlock the message, and they're good to go. And the math is very complicated, We're going to try to make it simple here. So you already know what a prime number is. A prime number is a number that can only be divided by 1 and itself. So the numbers 2, 5, and 7 are prime numbers. Number 20 is not a prime number. Number 9 is not a prime number because you can divide 9 by 3. So the private key is basically just 2 prime numbers, and you multiply them together, and that becomes a public key. And the reason this works so well is if you pick really big numbers, then it's very easy to multiply them, but very difficult to divide. If I gave you the number 7 and 11, it's pretty easy to come up with 77 as a product. But if I gave you the number 77, which is out in the public, and you gotta figure out what two numbers to multiply to get to 77, you're gonna have a bit of a hard time. Of course, the numbers are way bigger than this. So, if I pick two massive prime numbers and multiply them, and I come up with an even bigger massive prime number that's on the, not a prime number that's on the left, there's no way that you're going to figure out what two numbers you used to multiply to get to it and break the encryption. And of course, these numbers are tiny compared to the numbers that they actually use. So, when you use key lengths that are long enough to encrypt your data, it can never ever be broken, even with lots and lots of servers. But the math is actually even more complicated than what I just said. What actually happens is the classic Alice and Bob, and they need to send a message to each other. So the first thing that happens is Alice and Bob, they pick two numbers which we're going to call P and G, and we're going to use small numbers in this example because I'm going to try to keep it simple. So Alice and Bob pick two numbers that are prime numbers. They pick tiny numbers, and this is, everybody knows what numbers they picked. It's on the internet. And then Alice picks a number, we call it A, and Bob picks a number, we call it B. And these are secret numbers. Nobody ever figures out what they are, because Alice just writes this down in her computer, and Bob writes it down in his computer. And then they each calculate this number. Obviously, they're not doing this by hand. The computer software automatically does it without anybody knowing it. I mean, just ask your friends. There's nobody who actually calculates these things. Anyway, the math isn't actually that complicated. Alice basically just calculates capital A, which is G to the power of A mod P, and Bob calculates capital B, which is G to the power of B mod P. And if you're wondering, Alice gets the number 12 and Bob gets the number 10. And the reason is mod is basically just a remainder. That's all it is. So if I said 10 mod 2, what's 10 divided by 2? It's 5. There's no remainder, so the answer would be 0. If I said 11 mod 2, what's 11 divided by 2? It's 5 and the remainder is 1. So 11 mod 2 is 1. So if we look back at this, when Alice calculated A, she got 11 to the power of 12 and then divided that by 23, 11 to the power of 12 is a huge number. But Alice has technically 23 possible solutions, and so does Bob. So, if you pick a prime number for P that's massive, let's say 1 billion, then you've got 1 billion different possible remainders, depending on the other numbers. But I digress. So, Alice figured out what A was, and Bob figured out what B was. And they tell each other. So Alice says, hey Bob, A is 12, and Bob says, hey Alice, B is 10. Which is great, because then each of them calculates S. Which for Alice is capital B to the power of A mod P, and Bob figures out capital A to the power of B mod P. And then they get the same answer. And according to some mathematical theory, if you did this right, Alice and Bob get the same answer, which is 13. And 13 is a secret number. Of course, in reality, the number is massive. And now, the best part is, Alice figured it out by herself, and Bob figured it out by himself, and neither of them had to tell each other the secret key over the internet. They just shared G and P and capital A and capital B. But neither of them shared little a or little b. So the hackers couldn't figure out the number 13. So as I said, everybody knows P, G, A, and B. But P, G, A, and B aren't enough to crack the code. So P has to be absolutely massive in order to not be cracked these days, because they found that some supercomputers clustered together could even crack the value of P that was 1,024 bits. We're talking like $300 or $400 million investment. But a $300 or $400 million investment is not out of reach of some people that want to crack the encryption, especially the Russians or whoever. So, current recommendations are to use a P value that's at least 2048 bits, which is 2 to the 2048, which is basically like a number with 600 digits. Not joking. So the main problem is everybody's using the same value for P. And why is that? Because developers are lazy. So what happened was, the correct way to write your app would be, hey, I want to encrypt some data over the internet. So I need to write some code that figures out a value of P, make sure it's a prime number, and then use that and randomize it so every time the app is run it picks a different value for P. But the lazy way was that the IEEE published a guideline and they said, hey, here's a value of P that you can use. And then everybody that built their apps just hard coded it. So they wrote down P equals blah 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 blah. And so 2/3 of the VPNs and the sophisticated apps that are running all over the internet, they use the same value for P. And that's okay, because they're picking random values for little a and little b. And so it's not like it can be broken, except that eventually with enough computing power it can be broken. And once you've broken P for one value, you've basically broken 2/3 of the world's encryption. And that's not good. Even though, remember, you're keeping S, A, and B a secret. So, And how do you keep the Russians from spying on you? Well, the answer is the Russians have this formula for P. And it's, if you run it enough times, you can figure out what P is and you can crack the encryption. So like I said, use a very big value for P. Or, more importantly, there's a new form of encryption that hasn't been cracked at that level. It's called elliptical curve cryptography, and it basically uses curves instead of prime numbers. And they definitely can't see through that. But in a few years they probably will.